Okay, so the point of what I will try to explain today is that this interpolation problem by polynomials, but it's the more simpler one than we saw yesterday in the Euclidean plane. I will try to study the analogous problem in hyperbolic space. So I will spend the first hour to define what the hyperbolic space of dimension 2, the hyperbolic plane, is in the model that we are going to be using, and then to define what is our interpolation problems, what we mean by polynomials in hyperbolic space, and so on, what is called finite Blaschke problems. So the model that we are going to use is the Poincare disk, the Poincare model. So it's the space that the disk, open disk of radius 1, and then what is special about it is that it is equipped with a different Riemannian metric, not the Euclidean model. So it is equipped with this Riemannian metric, which immediately it means that if so, here is my disk. Here is center 0, and here I have a diameter. So if I have a curve gamma, suppose that it connects 2 points on this real axis, then the length of this curve, by definition, is this integral. And you can see that it only gets smaller if I replace instead of gamma, I take just the real part of gamma. So I project the axis. So this somehow it proves that the geodesics, so the diameters are geodesic, because any curve that does not lie in the diameter has bigger length than the same curve that is just the segment on the diameter. And of course, by rotational symmetry, all diameters, not only the real segment minus one is geodesic. All diameters are geodesic, and you can even this way you can even calculate the length. So by psi ZW is the arc length metric that arises from this Riemannian metric. So it's the infimum over all length of the curve. And with this observation, you can calculate the distance between 0 and some point. This is going to be just the distance between 0 and by rotational symmetry, the point is here. You can rotate it and put it on the real axis, and this distance is going to be the same. And by taking the curve to be this segment parameterized, we find that this is the integral from 0 to 1 times dt 1 minus dt squared, which you can calculate that it's the logarithm from 0 to 1 minus 0. So in this case, we know how to calculate the distance between 0 and any point. And the fastest way to proceed now is to proceed by hindsight. So I just define the automorphisms of this space of the hyperbolic field. The set of these transformations. So as I said, if you know what you're looking for, it's easy to write it down. But it will turn out that these automorphisms to disk are in fact isometries for the hyperbolic metrics. And this will be very useful for us. And we will solve it actually. So I will use this special notation for this. So we denote by tau A, this transformation that appears here. So up until now, it's not maybe it's not immediately clear that this transformation. I mean, they are defined. They are defined for Z in the unit disk, but it's not clear that they map the unit disk to itself or anything. So we're going to prove everything. And many of these properties follow by some algebraic relations, simple relations that this transformation satisfies. So, for example, one of the most useful ones is the following. So let's list here some properties. Okay. If you take some points that W in this, and some A, this, and you try to calculate this quantity. So then, this is 1 minus L minus 3. W, yes. And then in the algebra, here I find 1 minus 10, and then minus W. W. And I'll write it in 2 rows. And here, if you multiply out in the numerator, you find ZW. That's and sorry. Let's take the denominator. And here you can see that you get some cancellations between these fractions. So this cancels with that. This cancels with that. So in the end, you get 1 minus A squared and W divided by this one. And you get this very nicely factorized relationship. So the point is that immediately this tells us the following, that so if we take Z equals to W, then we find that 1 minus the modulus of tau A squared is something positive, right? Because this becomes positive. So in fact, when Z is a point inside, and when Z and A are points inside the unit disk. So in fact, the modulus of tau A is inside the unit disk. So it maps the space, the coordinate disk to itself. And on the boundary, if Z lies on the boundary, tau A is well defined on the boundary, then this is equal to 0. So in the boundary, tau A is of modulus 1. So it maps also the boundary of this to the boundary of this. Okay. And not only that, but you can, this calculation I will skip, but is also completely elementary. You can calculate the inverse of tau A, and it's exactly equal to tau of minus A. So in particular, by applying the inverse here, because these relations hold also for the inverse, then you get that tau A of B is exactly B, and tau A of the boundary is exactly equal to the boundary. It's a one-to-one map because it's invertible and it maps the disk onto itself and the boundary onto itself. Okay. And one last calculation that is relevant for this tau A is, so that was relation 1, relation 2, on this one. And the third one I would like to mention is to get to calculate its derivative. Then you get 1 minus, let's say, minus 35. So here you get a cancellation here, 1 minus the modulus of A squared. So in particular, we have this formula for the derivative of tau A. In particular, this will solve that these transformations are isometries for the hyperbolic space, because the modulus of the derivative is this. But by the relation that we have found above, this is exactly equal to 1 minus tau A squared divided by the squared. And if you rewrite it, putting the infinitesimals if you want, you find that exactly these are isometries for the Riemann metric of the hyperbolic disks, or are isometries of the space. Okay. And And okay, now using this tau A, we can find, for example, formulas for the distance of any 2 points. Just by, because this tau A, what they do is that they allow us to transport the origin to any point we like, right? So if you want to, for example, to calculate if you want to calculate the distance between Z and W in the hyperbolic space, then this is you can apply tau Z, for example, to both arguments because it's an isomorphic. And we know that this is exactly the logarithm multiplies the modulus of 1. And the point is, so this quantity here, the modulus of tau ZW, it also appears often in practice, and I am going to give it some name. So it can be proven that this quantity it's also a metric, not an arc length metric, but it is a metric, and usually it's called pseudo hyperbolic metric. It will appear more and more. Also, you can identify all geometrics. If you know that now that we know that these tau A are isomorphic, we can identify all possible geodesic vector space in the following way. Will not be super precise. So we know that diameter are geodesic. And we know that these tau A are Mobius transformation, fractional linear transformations that preserve the unit circle. And Mobius transformations also preserve angles. So, for example, if I take this geodesic, which is orthogonal to this to the boundary of the circle, and on this diameter, then it will be mapped by this Mobius transformation to some arc of circle, which must be also orthogonal. For example, if I apply some tau, let's say minus r, where I choose this A to be some r is a positive number. So this case minus r is I can see that because everything is real, it must preserve this this real diameter, and it must preserve all the angles. And you can see that it maps 0 to r. So the image must be a circle which is perpendicular to the boundary and to this real diameter, and it must pass from r. So it's the only circle arcs of circles that this stop. Okay. And then if I consider rotation, I can in fact take any arc of circle which is perpendicular to the boundary. and it lies inside in the unit dish. Okay, and with an epsilon more work, you can do it as an exercise. You can solve that these are all the geodesics that there exist. So also I would like to mention that so the hyperbolic plane, the group of isometries, the hyperbolic plane is a Lie group with two connected components, and the one is what I denoted by automorphisms of P. There's the connected component which contains the identity, and it consists, as you saw, of holomorphic maps, in particular linear fractional transformations. The other connected component is just so the other connected component of the isometry group of the hyperbolic space is obtained just by considering the one transformation that is missing here, which is the conjugation. So it's just given by composing Z bar automorphisms. These automorphisms. And these are all, you can prove that these are all the isometries that that hyperbolic space has. These are ones of the orientation preserving and the orientation reversing transformations. Okay, so that was pretty much everything that I wanted to tell you about the geometry of the hyperbolic space. And then, so here it comes a lemma. It's a very simple lemma, which tells you that really interpolation problems or even complex analysis is very different in hyperbolic space with respect to the Euclidean space. Okay. So this is the lemma. And so I will denote by P plus functions which go in this itself and holomorphic. And this extremely simple lemma, say lemma 0, says that if you take a function f from the disk itself holomorphic that fixes the origin, then you have the following. F of z is actually bounded by z. And the derivative at 0 bounded by 1. This is such lemma. And furthermore, equality occurs in one for some non-zero z for U2, then F is actually an automorphism of the unit disk. Okay. So I will prove the proof is sorted on the statement of the theorem. So I will prove it, and then maybe I can comment on it. So the proof is this. Very elementary. You just consider the function f of z divided by z. So by assumption, this function is holomorphic in the unit disk because it has the removable singularity and the origin, and then at the boundary, the limit sup of Z is less or equal than 1. Because the modulus of Z on the boundary is 1, and we know that F maps inside the unit disk. So by the maximum principle, bounded by 1 everywhere, implies that F of Z is bounded by Z, modulus of Z, and the value of Z at the origin is that the derivative of F at 0. So also the derivative of F at 0 is bounded by 1. In particular, by the strong maximum principle, if you have at some point equality here or there, then it means that you have equality in this inequality for some interior point. And then by the strong maximum principle, G must be a constant. A constant of modulus 1. Yeah, sorry, here not only automorphism, but that's the rotation. Yeah, G must be a unimodular constant. So F is just a rotation. So why I said that this simple lemma means that the things are different in hyperbolic space, because I mean it will be more clear if we, when I will do now the Schwarz peak variable dilemma, but also you can see it here. This means that if F fixes at the origin, then it must contract the hyperbolic distance between 0 and Z. So in some sense, no, in a very precise sense, the holomorphic functions are contractions of the hyperbolic distance, which for sure it does not happen in Euclidean space. Yeah, so let's write this also as a lemma. This is what I'm referring to as not lemma. It's exactly the same thing, but in different coordinates, let's say. So the hypothesis now is that F is the holomorphic self-map of the unit disk. Then we have that. Then for the 2 points, Z means that not the disk has that. So this one, which is that the pseudo hyperbolic distance between F of Z and F of Z 0. Is smaller than the pseudo hyperbolic distance between Z and Z0. So what I was saying before, in fact, holomorphic self-maps of the unit disks are contractions of the pseudo hyperbolic, and hence the hyperbolic distance between points. And there exists also the infinitesimal version of this, which says that have this inequality, and of course you can obtain the second from the first one just by dividing everything by modulus of Z minus Z naught and taking the limit at Z as Z naught goes to 0, as Z goes to 0. And if equality occurs somewhere, then F is an automorphism unit. And the proof is really just changing coordinates on the original Schwarz now. So we want to apply the usual Schwarz lemma. So okay, we have 0, which we can send it to Z naught for experimentation. Yeah. So we can send 0 to Z naught by applying tau of minus Z naught. Then Z naught will go to F of Z naught through F, which will go to 0 again if we apply tau of F. Okay. So if we compose everything here, we can apply the Schwarz lemma on the function g tau minus Z naught F. Okay. Which fixes the origin from this diagram, and we get that now composed E smaller than the modulus W, and I can, this is invertible, I can change variables again. I can set T W equals T of Z naught of sample Z, and this will give me exactly what I want. Which is the first statement of the theory. Okay. Now, if you divide Z by Z times Z naught, you get the infinitesimal vector. And if you have a quality occurring somewhere, you can solve that you will have a quantity occurring for G in the same point. So you get that G is a rotation. Which will imply that, so by composing with the inverse transformations, it implies simply that f of z is tau of the one applied to the and this is an automorphism of the unit disk as a composition of automorphisms of the unit and this solves this theorem. So the moral of the story, apart from the calculations, I think, is that since so holomorphic self-maps of the unit disk contract the hyperbolic distance, we cannot expect to interpolate even arbitrary couples of points. Okay, so because if I have 2 points in the hyperbolic space here, and I want to interpolate them by a holomorphic self-map of the unit disk and send them to two points in the hyperbolic space there, then if this distance is if this distance here is bigger than this distance, then it's going to be impossible because my map F is a contraction, so it cannot happen. And you can see that for a couple of points, you can do it by using these automorphisms in tau A. For a couple of points, this is an if and only if condition. You can interpolate, you can send these 2 points to another 2 points with a holomorphic self-mount of the unit disk, if and only if their hyperbolic distance of the images is smaller than the hyperbolic distance of the pre-images. So Peake's problem, and what we're going to see probably in the next hour, is what is the necessary and sufficient condition in order to send endpoints in the hyperbolic space to other endpoints in the hyperbolic space. And we will see that if you can do it with a holomorphic map, then you can do it in fact with what is called the finite Blaski product, and it's the analog of a polynomial in a hyperbolic space. But maybe we can do a small break here and then continue in 10 years.
Yep.
Sorry, what are the analog of polynomials for hyperbolic space? What have you said?
But I say finite Blaski products for me.
Okay. Okay, thank you.
Okay, we take a 10 minutes break.